In this paper, the authors extend their previous analysis of quantum gravity in a general background gauge to include finite temperature effects. They calculate the leading logarithmic contribution from the graviton self-energy at one loop order, providing an analytic expression that smoothly interpolates between the zero and high temperature limits. This result is then applied to evaluate the thermal corrections to the gravitational potential in a general background gauge, generalizing the previous result obtained at zero temperature. The magnitude of the quantum correction decreases as the temperature rises. This work contributes to the ongoing efforts to treat general relativity as an effective field theory, which may lead to predictive quantum corrections at low energies. In this section, the authors elucidate the properties of thermal quantum gravity within a general background gauge. They initiate their discussion by introducing the Einstein-Hilbert Lagrangian for the theory of quantum gravity, which is predicated on the curvature scalar and the metric tensor. The metric tensor is then decomposed into a classical background field and a quantum field, with the background field vanishing at infinity but being arbitrary elsewhere. Subsequently, the authors expand the Lagrangian in powers of the quantum field, thereby obtaining a quadratic part that contributes to the graviton self-energy. This contribution encompasses terms related to the covariant derivative, the Ricci tensor associated with the background field, and gauge fixing and ghost Lagrangians that preserve gauge invariance under the background field transformation. To extend this theory to finite temperature, the authors employ the imaginary time formalism, where the energy assumes discrete values due to periodic boundary conditions for bosonic amplitudes. This results in a single Bose-Einstein statistical factor, which separates the amplitude into a zero temperature and a temperature-dependent part. The thermal part can be represented as a forward scattering amplitude with an internal line cut open to beyond shell, accompanied by the corresponding statistical factor. The real-time result can be obtained through an analytical continuation of the external energy. This method is demonstrated in the subsequent section for the graviton self-energy at finite temperature. The authors of the research paper focus on the thermal graviton self-energy, presenting the Feynman diagrams contributing to it at one loop in Fig. 1. At zero temperature, the singular terms for d equals 42 epsilon can be written in the transverse form, as shown in EQ. 3.1. This expression is obtained by using the fact that in a general background gauge, the result can be expressed in terms of combinations of three types of integrals, EOB, K, as defined in EQ. 3.3. The singular contributions of these integrals can be related as in EQ. 3.4, and the singular coefficient in EQ. 3.1, can be expressed in terms of I-div 11, as defined in EQ. 3.5. To extend these results to finite temperature, the authors express the corresponding contributions from the diagrams in Fig. 1 in terms of the forward scattering amplitudes shown in Fig. 2. These thermal contributions can be evaluated in terms of three types of temperature-dependent integrals, I-tab, K, as defined in EQ. 3.6. This approach allows for a comprehensive analysis of the thermal graviton self-energy, providing insights into the behavior of gravitons under different conditions. The thermal graviton self-energy integrals are evaluated in terms of logarithmic functions and Riemann's zeta functions, focusing on the leading thermal logarithmic contribution that reduces to the log k squared term in the zero temperature limit. This contribution is expressed in terms of I log T11, calculated as a function of logarithmic terms, as shown in equation 3.9. The result vanishes in the zero temperature limit, as expected. By combining the contributions from equations 3.5 and 3.9, the log k squared terms cancel out, and the total leading logarithmic contribution from the graviton self-energy is obtained by extending the zero temperature result in equation 3.1 to equation 3.10. This expression has been explicitly verified for the log t squared contribution at high temperatures. The thermal graviton self-energy corrections to the classical gravitational potential are evaluated by coupling the external background field to the energy-momentum tensor of the matter fields, using the Lagrangian for scalar fields in equation 4.2. The energy-momentum tensor is given by equation 4.3, which yields the graviton-matter coupling in momentum space, equation 4.4. This sets the stage for calculating the quantum correction coming from the diagram in Fig. 3a. The resulting expression enables the calculation of thermal corrections to the classical gravitational potential, providing a vital step towards understanding the interplay between gravity and matter at finite temperatures. The authors extend their previous work on one-loop corrections to the gravitational potential at zero temperature to finite temperature, focusing on the thermal graviton self-energy. This key component of the total thermal correction is calculated in a general background gauge, using the Feynman diagrams depicted in Figure 3. The thermal part of the graviton self-energy, delta Vt, is derived using the transversality of the graviton self-energy and the background field propagator, resulting in a logarithmic contribution to the potential, as shown in equation 4.5. In the non-relativistic static limit for two heavy particles with mass m, the expression for delta Vt in momentum space is obtained, given in equation 4.6. This is then transformed to coordinate space using the relation in equation 4.7, yielding the thermal correction generated by the graviton self-energy, expressed in equation 4.8. In special gauges, such as those where sigma equals 2 pi 13 equals 3, the thermal contribution from the graviton self-energy matches the complete result obtained in the gauge sigma equals 1, as found in refs 11, 12. The full thermal correction to the Newtonian potential is thus given by equation 4.9. The ratio R between the finite temperature and zero temperature corrections is plotted in Figure 4 as a function of x equals 4 pi RT equals tilde C, illustrating the significant difference between the thermal and zero temperature corrections to the gravitational potential. The author's work extends their previous results at zero temperature to finite temperature, highlighting the importance of considering the thermal graviton self-energy in calculations. The paper concludes with the complete leading thermal correction to the Newtonian potential, which is gauge-independent and physically meaningful. The authors of the research paper delve into the relationship between the ratio R and the parameter x, which is proportional to temperature T, as depicted in Figure 4. This ratio is closely tied to the graviton self-energy and converges to the known result at T equals 0. The transversality of this term stems from the theory's invariance under background field transformations. The logarithmic factor in the equation is gauge-independent, suggesting that its branch cuts might correspond to physical processes that occur at finite temperatures. By applying equation 3.10, the authors calculate the leading correction to the Newtonian potential generated by gravitational vacuum polarization at all temperatures. In special background gauges, they derive an analytical expression that generalizes the full result previously obtained at T equals 0. This expression involves the quantum factor g, which is typically very small but could become significant at shorter distances. The authors observe that the quantum correction decreases as the temperature increases, a phenomenon that can be understood by adapting an argument provided by Feynman. As the temperature rises, the field lines connecting the two particles spread out, reducing the gravitational force between the particles and leading to a decrease in the magnitude of the corrections. Despite the unpredictability of quantum gravity at high energy, the authors confirm that one can make calculable physical predictions at low energies, supporting the general effective low-energy strategy implemented in the literature. They also mention an alternative method of quantizing general relativity, which leads to a renormalizable and unitary theory. In the appendix, the authors examine the behavior of the temperature-dependent integrals ITAB, k, defined in equation 3.6. They focus on the integral IT11, k, and express it in terms of x, the cosine of the angle between k and pages. They then evaluate the integral using a change of variables, resulting in equation A1. The evaluation of three integrals, IT11, k, IT12, k, and IT22, k, is a crucial step in calculating the graviton self-energy. These integrals are evaluated using the integral reduction method, which allows for the expression of tensor integrals in terms of scalar integrals EOB, k. The leading logarithmic contributions to these integrals are determined, and infrared divergences that arise due to this method are addressed by subtracting and adding terms with p equals 0 in the denominator. This process ensures that the graviton self-energy remains infrared finite. The integral IT11, k, is transformed into a more manageable form using a change of variable, k, x, and then evaluated using a p integration. The result is expressed as a function of k, involving the digamma function and a surface term that leads to the final expression in equation, A5. The integral it12, k, is also evaluated using a similar approach, involving a change of variable and p integration. However, it is infrared divergent, which necessitates the subtraction and addition of terms with p equals 0 in the denominator to ensure infrared finiteness. After performing the p integration, the result is expressed as a function of k, involving logarithmic terms and a surface term, as shown in equation, A10. Finally, the integral it22, k, is considered, and its evaluation involves a change of variable and p integration. The leading logarithmic contribution is determined, and the infrared divergence is addressed in a manner similar to it12, k. The final result is given in equation, A11, which includes logarithmic terms and a surface term as functions of k. In summary, this page provides detailed calculations for evaluating three key integrals in the context of graviton self-energy. The integrals are transformed and evaluated using specific techniques to handle infrared divergences, resulting in expressions involving logarithmic terms and surface terms as functions of the variable k. We focus on calculating the leading logarithmic contributions to the relevant terms, specifically examining the expression in equation, A6. Analysis reveals that only the first term is relevant, which can be computed similarly to previous methods. The leading logarithmic contribution, denoted as I log t22, k, is calculated as I log t22, k, equals 2k 4/16 pi caret 2 log t squared k squared t 4 pi ij tilde kj log 1 plus k plus t 1 plus kt. By utilizing equations, A5, A10, and A12, we verify the relation in equation 3.7 and express the relevant logarithmic contributions solely in terms of those appearing in I log t11, k. To further analyze the expression, we employ the series representation for the log 1 plus k plus t, 1 plus kt term. Log z equals z log z, z1, 2 log z, plus log 2 pi, plus infinity summation 1 per meter, m plus 1, m plus 2, infinity summation 1, n, z plus n, caret, m plus 1. Where z equals 1 plus k equals t. This representation yields the following logarithmic contributions. 1/2, 1 plus k 0 halves pi it, log k plus t, kt, plus j tilde kj, 4 pi at log 1 plus k plus t, 1 plus kt. Substituting this expression into equation, A5, yields the leading logarithmic term. I log t11, k, proportional 1/16 pi caret 2 log k squared, 8 pi I k0 t plus 16 pi caret 2 t squared k squared. Notably, this expression vanishes in the zero temperature limit, as expected for purely thermal contributions due to the statistical factor. This term contributes to the expression in equation 3.9. After cancelling the log k squared with that present in equation 3.5, the remaining log k caret 2 8 pi I k0 t plus 16 pi caret 2 t squared term can become significant for very small values of k squared and t squared. In the static limit, k0 equals 0, such a contribution would dominate over other contributions arising from the series representation. Quantum field theory, QFT, is a fundamental tool in understanding the behavior of particles at high energies. This paper explores the application of QFT to quantum chromodynamics in two-dimensional spacetime, focusing on the Gross-Neve U model. The Gross-Neve U model is a quantum field theory that describes the interactions between fermions and scalars, and it is crucial for understanding the phase structure of the theory. To compute the effective action for the scalar field, the authors employ the Feynman trick, which simplifies the calculation. They also discuss the role of the renormalization group, emphasizing its significance in determining the behavior of the theory at different energy scales. The beta function, a key concept in the renormalization group, is used to analyze the stability of the theory and identify possible phase transitions. The paper presents numerical results for the effective action in the beta function, obtained using a combination of analytical and numerical techniques, including Feynman diagrams and the Schwinger-DeWitt propertime representation of the heat kernel. These findings are compared with previous studies, and potential implications for our understanding of quantum chromodynamics are discussed. The paper concludes by summarizing the main results and outlining future directions for research. The authors emphasize the importance of further investigating the phase structure of the Gross-Navier model, as well as exploring other quantum field theories using similar methods. This work provides a detailed exploration of the application of QFT to quantum chromodynamics, shedding light on the complexities of particle interactions at high energies.